Hi, everyone, and welcome to the IDSS Distinguished Colloquium. It's my pleasure today to introduce Lisa Goldberg. I think it goes without saying that Lisa wears many hats. She's head of research at Apereo. She's a managing director at BlackRock. She's a professor of practice in economics at Berkeley as well, and also the director for the Consortium for Data Analytics in Risk, also at Berkeley. She's a mathematician by training, has worked in many areas on dynamical systems, quantitative finance, high-dimensional statistics. I think today we're going to hear something that's at the intersection between quantitative finance and high-dimensional statistics. Among the other caps that she wears must be a swim cap, because her bio says that she's on track to swimming 40,000 miles around the equator. Kilometers. Oh, are you Canadian? Like metric, okay. It's less impressive if it's kilometers.
It is,
so.
it's the equator.
Ah, I see, good point. Okay, so please join me in welcoming Lisa.
Thank you. Thank you for the kind introduction. It's of course a pleasure and an honor to be here at MIT. Great also to be able to talk about this material that I love and have been working on now for quite a while. I'll get to represent the work of quite a few people, and we'll try and mention names as I go along and also show some pictures at the end. But there are two names I want to mention whose work goes throughout this presentation: Alex Skolnick and Alec Kercheval. So they're instrumental in all the things that I'll say today. The thing I'd like to do is talk about two very important and very influential theories that were developed in the 1950s. So this is not new material by any stretch of the imagination. What's new, if it's new at all, is how they come together. These two theories don't sound very much alike and don't seem to have a lot to do with each other, but they merge in an interesting way, and that's, the names are Harry Markowitz and Charles Stein. I think Willard James, who's the James and James-Stein, of course, is also very important. So in talking, it's been so fun all day to talk to members of IDSS who've come around and see what people know and see what their backgrounds are. And always reminded, I'm a little bit glad that I'm starting at the beginning here with something pretty basic to anybody who would be like in the Sloan School of Management or in a basic financial economics course, but I don't know that lots of scientists are familiar with this guy, Harry Markowitz. I don't know exactly how old he was when this picture was taken. He's 95 now. He's in San Diego, he's still working, and in 1952, he did something that is remarkable, and well, he did many remarkable things. In 1952, he did the first of many remarkable things, and something that affects all of us today, I think, whether you know about it or not. If you have an investment, if you have a retirement account, if you have an ETF, if you have any type of participation in today's financial system, you are being held up by Markowitz's ideas. He is sometimes thought of as the father of modern financial economics. And I will show you the thing that he is first famous for and most famous for, which is this red quadratic curve here. So Markowitz's first contribution was a paper in 1952 called Portfolio Selection. And what he did, which may seem very obvious with hindsight, is frame investing as a trade-off between something that we like, more return is on the y-axis, and something we want to avoid, which is risk, which you've got here on the x-axis. And he explained that since you want to avoid avoid risk and get expected return, that you want to take a particular risk level, get as much return as possible, or equivalently take a particular return level and get it for as little risk as you can avoid taking, meaning you would like your risk-return profile of your portfolio to be on this red curve, and you don't want to be down here. Of course, you'd love to be up here, but there aren't any portfolios there. They just don't exist. So this is where your investments should be. This is the efficient frontier. And it's worth saying, this is a two-dimensional picture, how you get from a portfolio to a point in a plane. And what's a portfolio anyway? Well, it's a complicated thing, but for the purpose of today, I'll think of it as a big vector. You have some money, think of it as $1, and you want to put a part of your dollar in different securities. So you put 2 cents in General Electric and minus 3 cents in Apple Computer, or whatever it is, that vector of your allocations or your fraction of your allocations to different securities, that's your portfolio. And the rule is it has to add up to the amount of money you started with. That's 1. But it can be plus or minus. And how do I get from that long vector to a picture in this portfolio? Well, to get the y coordinate, I take my vector and I take its dot product with another vector that I'm supposed to know, expected returns of each security. I expect G to return 1% next year, and I expect Home Depot to return minus 4% next year, whatever it is. There's this vector. I take the dot product with my weights vector, which is describing the portfolio. I get a y coordinate. The x coordinate is a little more complicated. You take your weight portfolio, describe the weights of your portfolio, and you pre and post multiply a covariance matrix with that vector and take the square root. That's a standard deviation. Okay, so every portfolio, which is a long vector, gets mapped to a point in this plane. The best ones are along here, according to Harry Markowitz. None of them get mapped here. Lots of them get mapped there. This is kind of an early dimension reduction, non-linear dimension reduction. A lot of dimension reduction today. I don't know if Markowitz thought about it that way at the time, but it was kind of a good idea. So that's, a historical note. In his 1952 paper, which has got many great illustrations, this is not among them. The earliest I've ever saw a picture like this is in Markowitz's 1959 book, and the axes were transposed, but maybe there's another one. I don't know. That's the earliest one. Even though this picture's not in the paper, it's come to be the poster child for how you want to invest, mean variance optimization, efficient portfolios. So there's this, I'm interested in all those portfolios and lots of others, but there's one special one here, minimum variance. In a universe of risky securities, and really there's no such thing as a risky security anyway, this is the smallest variance, the smallest standard deviation portfolio. And to get all of the portfolios on the slide prior to this one, you can write a simple program like this. You want to minimize variance. Here's the weight vector that I talked about, describing the portfolio, the covariance, subject to full investment. That means the numbers all have to add up to 1. There's no expected return in this particular point. It makes it the simplest portfolio, and it's a good one to focus on for the material that I'm going to talk about today, but we can put that back in later if it's important to you. Now, this is a very simple thing to solve for if you're taking linear algebra. You can write a closed form solution. So why should this be the center of a talk at MIT? The answer is that we don't really know what that sigma is. We just have to estimate it out of data. So in reality, we have a sigma hat instead of a sigma, and instead of getting an optimal portfolio, we get merely an optimized portfolio. And that's a problem. So in this 1952 paper, Markowitz worries about a lot of things, and maybe it's because he worries about these things as part of the explanation for why his ideas have been so successful. He formulated portfolio investing in a particular way and then set about to make the thing work. So Markowitz has a Nobel Prize for his ideas, and he also has a John von Neumann Theory Prize for Computer Science for his implementation. In fact, you don't need a computer program to compute this particular portfolio, but when they get a little more complicated, as they already did in his early paper, you needed an algorithm. What do we do when we need an algorithm today? We go to a Python library, or maybe we write our own. But back in 1952, this was like a big deal, getting algorithms to take information and compute things. And he developed algorithms to solve the problems he was interested in. He also was very worried, even as early as 1952, that he wouldn't be able to get the inputs to his program. So it's kind of this holistic approach to problem solving that is one of the things that I like to think about when I think about Harry Markowitz. So in classical statistics, it's a great thing. We have a lot of observations and very few variables. And investing, the variables we wanted to get are like the weights of that portfolio vector, and there are a lot of securities. You need a one weight for each security. So we end up in a high-dimensional problem. And Markowitz was very clear that he did not have the data that he needed to apply classical statistics. And this is a quote from his paper, one of many interesting ones. The calculation of efficient surfaces might possibly be of practical use. Perhaps there are ways by combining statistical techniques and the judgment of experts to form reasonable probability beliefs for the expected returns in the covariance matrix that he needed. So often running financial services has devoted, I don't know what kind of effort, time, money, it's incalculable, to creating these sigma hats. There's a big industry of it. A company you might have heard of called Barra is kind of the industry standard for making such things for equity models. And there's lots of different ways to think about the problem of estimating a sigma hat that you can put in a Markowitz optimization. Now, it's a problem because you have a sigma hat. It's only an estimator. You may not know exactly where the errors are. And when you take something with errors in it and put it in an optimizer, what does the optimization do? It finds those errors, and it expands them, and it distorts them. There's a paper that I like by Richard Michaud, who's a local scholar and also businessman, and also one of the members of our community who's trying to keep financial services industry intellectually honest, which is not an easy task. As I'm sure he would tell you if he were here, mean variance optimizers are estimation error maximizers. Optimization amplifies whatever errors I got there. So if you want to know how the optimal and optimized portfolios differ, well, the answer is a lot, and I'll show you how much. But optimized sounds so good, but it's really maybe not that good. It can be very different than optimal. So when I want to make a sigma hat, a natural starting place for me would be to take the data that I have and create a sample covariance matrix. And we do this all the time, right, in statistics. And when p, the number of variables, is large compared to the number of observations n, even if it's not larger than, but especially if it's larger than, this s, which I'll use this symbol throughout for a sample covariance matrix, can be a problem. So here's s, and it is made of covariances, sigma ij. It's a square matrix. The covariance between variable I and variable j. And a natural way we think about this is as a product of two volatilities in a correlation. Those are very interpretable numbers. When I'm talking to anyone in science or I'm talking to anyone in finance, and I tell them what a standard deviation is approximately, or a correlation of 0.3, something comes to their mind that usually makes sense to them. But there's another way to describe a sample covariance matrix, or indeed any other covariance matrix or any Hermitian matrix, which is through its spectral decomposition. And I'm assuming and hoping anyway that this is familiar to most everybody in the audience. You write this same expression, not just in terms of its covariances, you write it as a sum over eigenvectors. Eigenvectors are directions that explain the maximum, as much variance they can. For example, the first eigenvector h is a linear combination of variables that explains the most observed variance. And the second eigenvector, which I've written down here, is given among vectors orthogonal to the first one, the one that explains the most residual variance, and so on. These are eigenvalues associated to the eigenvectors. They're numbers. So this is an outer product here, a number times an outer product. You sum this thing up, you get the matrix back. This is a very handy decomposition, and I use it like a spare parts store to create sigma hats that I can actually use in optimization. In all of the cases that I'm going to be looking at, this S is singular, so I could never use it in the optimization. There's a matrix inversion. You can't invert that thing. So I will take those pieces. OK, so we'll tell the story in a second of a research project that we began about 6 years ago or so, but just start by saying a little bit of some of the things that we found. Our goal was to find out the difference between optimized and optimal in a setting that's commonly used by financial practitioners. So the first thing that we found out is which are the errors. S is full of errors. The error that mattered when we put the sigma hat that I'm going to construct for you in an optimization was in the leading eigenvector. And the leading eigenvalue and that other stuff that I graded out because it didn't matter. This was a very surprising result because if you're familiar at all with random matrix theory, Dan, is a study of eigenvalues. There's a huge amount of study of the lambda squared and the lambda squared k's for k larger than or equal to 2. And I'll talk a little bit about it. When we initially tried to explain the difference between W star and W star hat, we started by looking at those, and we didn't get anywhere. So errors in that eigenvector make a great deal of difference in optimization. Errors in eigenvalues didn't matter. So an eigenvector is actually a line through the origin. It's even not a direction. It can go up or down. An eigenvector is just a dimension. But I'm going to write eigenvectors just for convenience as though they had a sign. I'm going to write them on a sphere. And I'm going to show exactly how I'm going to take error out of an eigenvector that's relevant to observation. So on this sphere, which you can think of as, say, like a 700 sphere or a 3000 sphere, or however dimension that you like, my observed eigenvector is this red dot over here, somewhere on the sphere. And the true eigenvector that I don't observe, that would be part of the actual matrix, the noise-free one, is this green one here. And what we found is that if you add a point on the sphere that's vaguely in the neighborhood, it has to be in the, there's actually no condition, but I've drawn it in the same hemisphere as this green one, and you always can, that if I connect the observed dot to, this is my sample, to the point that I added, and shrink in by just, well, With almost surely, this dot will be further away than the truth, and that if I shrink in to a point where I get a right angle between the true vector and this line here, I've taken out the relevant component of estimation error. So that, again, this is observed, this is hidden, this is a point I just made up and added, and if I shrink along that geodesic by just a right amount, I get something much better. Now, of course, if I knew where to draw that point, I used the unobserved vector, I would have just gone there in the first place. Why would I have bothered with something incorrect? Well, the rest of the part of the theory says that we can find that place without knowing the green dot. It's data-driven. So there's a data-driven version of this point that I can get to along a geodesic between an observed point and a random point that I added. And I improve proximity to the truth pretty much no matter where I put that extra point. Sort of like James-Stein, if you know it. So that's number 2. Yeah?
So in James-Stein, just for vectors, you normally shrink to the origin or you shrink to a subspace. Like you're saying you're going to shrink to some arbitrary point on the sphere?
I am. It's got to be in the same hemisphere as the green one, but since an eigenvector is really directionless, there's always one that's there. This, if I were to write this as I'd like to, I'd write it in projective space, but then I would lose a big part of the small audience I already have. So we try and stay on the sphere. But yeah, you just put it, well, in James-Stein, you can, James-Stein shrinkage works in any direction. Now, the results that I'm going to show, it's really quite amazing. The results that I'm going to show are guaranteed almost surely in the high dimension, low sample size regime, which is not a place that people usually go. But if you think about finance, where you have lots of securities and very few observations most of the time, unless you're doing high frequency trading, or in genomics, where you have lots of SNPs and not very many people in your lab to snip out of, or if machine learning, where we're trying to predict incredibly complex phenomena that might be driven by millions of variables, but we don't have lots of observations of it. This shape of a data set is not so unusual, and it's the shape that I'm going to focus on. And the results that I have are, this is here, unlike James-Stein, they're guaranteed almost surely in a regime where n stays fixed or grows very slowly and p goes to infinity. So this is an odd regime. It's not the usual regime of random matrix theory. But I will talk about how it fits with it a little bit. So I want to, we're going to measure, introduce 2 measurements, and then show you an experiment that set us on our way. So how do I measure? We had 2 portfolios, the optimized and the optimal, that's W star hat and W star. How am I going to measure the difference between them? And this is going to feed throughout the rest of the discussion. I'm going to borrow 2 metrics. So as Martin was saying, I spend 90% of my time in BlackRock and 90% of my time at Cal. So I take stuff when I can out of the financial services industry and bring it over to academia whenever possible. If I have a W star and a W star hat and want to know how far apart they are, what I'm going to do is take their difference and pre and post multiply that difference with their true covariance matrix and call that thing tracking error squared. Tracking error squared, or tracking error, is used everywhere in financial services, generally to tell how far a portfolio is from its benchmark. If you've ever invested, you might have had a benchmark like the S&P 500 or the MSCI ACWI. You have your portfolio. You want to know how close is my portfolio. Use a formula like this, but instead you use the estimated sigma that you have and the weights from 2 observed portfolios. I'm going to run simulations so I know the true sigma, and I'm going to ask truly how far away is my optimized from my optimal. So this is a very familiar metric. They could really put any quadratic form in there that I wanted, but this one gives me numbers that are intuitive to the practitioner part of my brain. The second metric that I'm going to use is the following. I have this optimized portfolio. I don't really know yet how close it is to the truth, but I can compute its variance forecast with my estimate and divide that by its true variance. So this is telling me what fraction of variance of whatever thing I've gotten out of that optimization am I actually seeing in practice. So this is a distance, how true or wrong are my weights, and this is how good is my variance forecast for whatever I optimized. The best number over here is 0, and the best number over here is 1. So those are two metrics to use in order to assess. And back in 2017, we were trying to make the tracking error squared go to 0 and the variance forecast ratio go to 1. We were looking at the problem of minimum variance with different types of sigma hats that we would construct. And I was working then a lot with Alex Skolnick, who I also mentioned, and Alex Papanikolaou. Maybe some of you know his father, George Papanikolaou, who's at Stanford. Alex is also a mathematician, a very fine one. And those guys, both Alexes, are super experts in probability theory and in computation and in convex optimization. And we were learning random matrix theory, and we would whip up all kinds of sigma hats, and they were so good that we could just whip up anything, and instantly they would implement it. And we would test to see whether we were making portfolios where the optimal was not too far away from the optimized things we were getting. And it was a lot of fun, but we failed, and we failed, and we failed, and this reminds me of something I know of the difficulty of an undirected search in a high-dimensional space. We got exactly what we would have expected from that. And after, try number 400 or something, a colleague of ours, Stephen Bianchi, showed up with the following experiment. He created 1,000 fictitious universes of data that he generated with a one-factor model that I'll show you in a second. Here I've just drawn 4 of them. And then he used each one to create an estimated covariance matrix using a PCA-type model that I'll also explain in the next slide. And he used each of those things to solve that very simple Markowitz problem for the minimum variance portfolio that I showed you a few slides back. So we have 1,000 of these, we have 1,000 of these, we have 1,000 of these. Here's the generating process, something very familiar. So many papers I read start with a little formula that looks like this. You have a one factor, you have some sensitivities to it, you have some specific excess return. So with this formulation of your data, your sigma, your true covariance matrix, looks like a nice sum. And so long as the factor return and the specific returns are uncorrelated and the specific returns are pairwise uncorrelated and have a common variance. I've got 3 variables, 2 numbers, a sigma squared, a delta squared, and 1 vector, a beta, that I've got to estimate. So my estimator, sigma hat, is determined by these 3 guys. That's the game. And here's what Stephen did. He created that PCA model using the betas with the beta was the leading eigenvector. He used the eigenvalues to estimate the variances in a standard way. And when he ran his experiment, he found tracking errors of about 2.5%. This is his experiment. And he found that he was getting about, when he used that covariance matrix to estimate the variance of the risk of his optimized portfolio, he got about 70% of it, which is not very good. So you were a distance away. The optimal portfolio and the optimized portfolio were this distance away, and you were under forecasting the risk significantly. Then he took the true eigenvalue, he corrected the eigenvalue with the truth. After all, it was his simulation, and left in the wrong eigenvector, and he got results that were completely unchanged from when he had not corrected the eigenvalue. When he left in the wrong eigenvalue and put in the correct eigenvector, he found that he got optimized portfolios that were much closer to optimal, and the variance that we were forecasting for them was very accurate. And so we knew that regular old random matrix theory, which corrects spectrum of eigenvalues, which had powered all of those hundreds of experiments, weren't going to help us, and that we had to correct an eigenvector, but we didn't know how. So this is Stephen Bianchi's experiment. Okay. Error in the leading eigenvalue of the sample covariance matrix, at least in the experiment that Stephen did, was not transmitted. Error in the eigenvector was transmitted. We wanted to correct it. So here is a picture from a recent paper that Alec Kercheval and I wrote. It came out in January. And it talks about the framework in which we were able to correct that eigenvector. So here we are in the halcyon land of classical statistics, where we have a small number of variables that we want to estimate with a huge number of observations, and our estimates are reliable, so long as we're drawing from the stationary distribution and so on. And here is random matrix theory. So this comes to us in the 1950s and the 1960s from luminaries like Wigner and Marchenko and Pasteur, and also Charles Stein has a very early paper talking about what happens when P and N are both large numbers. And if you don't know this theory, it's really beautiful. What happens is that there are universal limiting values for the spectra of eigenvalues as the dimension that you're looking at and the number of observations go to infinity in proportion. And this has been an explosive theory in physics and in engineering and in statistics and in all sorts of things, tons of applications. But there's another theory over here, which I call the HL theory, where you have a lot of observations, where you have a lot of variables and very few observations. And I've drawn it over here in a curve because you might think, well, if it's bad or complicated or mysterious over here, where both of these are large, when you've got a lot of variables and not many observations, that must be much worse. So I initially thought. But it turns out not to be the case. It actually gets easier. And the reason is that there are some circumstances where you can interchange the values of these two. Their roles can be swapped, and then some of what we know about classical statistics can be brought to bear on this. So an example would just be creating eigenvalues, right? If you have a P by N matrix, you take it times its transpose, you get a huge P by P matrix. You compute its non-zero eigenvalues. You can get the same eigenvalues by just switching the order of multiplying those matrices together. And now you've got P observations effectively determining the N eigenvalues, and they're very, very much better estimated. So this, in some cases, informs this regime over here. This is not, we've kind of noticed this, and then we noticed that a lot of other people had noticed it too. There's a literature on this that goes back to, at least as far as is a Hall, Neiman, and Moran paper from 2005. Researchers An and Jung-Yoon An and Sung-Kyu Young in Korea write about this. And Chaim Bar, who's here with us today, uses this idea in a beautiful paper that is doing something different then we are creating different statistical algorithms, but using the very same ideas that we use in our proofs to get the results that we get. So this is kind of growing in becoming noticed. Okay, so our first result is over here, like the purple picture that I showed you before. I'm going to get more specific here. H is going to be the observation again. B is going to be the truth. Z is going to be an external point. In this example, for the minimum variance portfolio, I'm going to let Z be the unique dispersionless positive vector on the p-sphere. So it's 1 over root p, 1 over root p, 1 over root p. It's that guy. And with probability that tends to 1, in an asymptotic setting where I have like a spiked factor model, like the kind of Ian Johnstone talks about, and that comes right out of the one-factor model that I was describing earlier, H is farther away from Z than B. A very high probability at dimensions that I care about, but asymptotically the probability goes to 1. The results are all almost sure. Our proofs are all law of large numbers proofs, but so there are no Gaussian distributions. There's no distributional assumptions whatsoever. There's a factor model shape, but no distributional assumptions. Now, to think about why this might be true, we use statistical methods to prove it, but there's also a different way to prove it, equivalent way to prove it, maybe with concentration of measure arguments. So if you, in dimension 2, where I draw spheres, there's a lot of mass near the poles. But in high dimensional spheres, practically all of the mass is near any particular geodesic. So the point here is that as p gets very large, if I think of an estimator of b, the probability of being inside this circle is much less than the probability of being outside of it. And as p goes to infinity, the ratio between the inside arc and the outside arc goes to 0. So you can reprove everything we've done with concentration of measure arguments. We didn't write it that way. So that's excess dispersion in the estimated eigenvector. I used the point, it was the first point we worked on, which was the dispersionless point. But as I was saying, you can put on any other point you want and have dispersion relative to that point, and the same thing is true. The second result, coming back to how this relates to optimization, involves this formula here, which is B is the truth, Z is the extra point we added. In fact, you could think of this whole theory as us adding an extra point. That was our contribution. It's a funny-looking formula, but it turns out that it controls, even though I had this optimized portfolio that I built with an estimate, its variance is controlled by this quantity. And in fact, I can approximate all these numbers and make a data-driven estimate of this thing too. The variance of the optimized portfolio that I built with a PCA model based around H is controlled by this quantity here. We call it the optimization bias. You can remove the optimization bias by putting in your estimator H just to be a B. But you can also zero this thing out with this guy over here. Nowhere near the truth. It's over here on the geodesic between the observed and the extra point. I put a right angle there. I take that H tau star. It zeroes out the optimization bias. Of course, as I said before, if I knew how to draw that, I'd know B, and I wouldn't bother being over here. I would have just gone to the truth, which is even better. But it turns out that we can approximate this thing very accurately with data. We call it the JSE, James-Stein for eigenvectors, estimator, and while it does not zero out the optimization bias at any finite point, it does asymptotically, almost surely, in this regime where the number of variables gets very large and the number of observations stays fixed, which is like everyday situation in finance.
On this process, what would happen if you did it a second time?
It did what a second time?
Choose another random point and did the same action.
Choose another, where am I in the process? I have my data.
You've sort of, well, I'm imagining, maybe I'm putting words into your mouth, that you're starting with your old estimate and you're going to sort of move it up to that new point.
Every path,
Yeah.
there's no algorithm here. There's an exact amount by which I move it on the path. If I had a different estimate, I move it an exact amount on that path.
Right. I'm asking if you do it this whole process a second time with another random point. Can you do that?
They're all, yeah, that's what the simulation is, right? Those are all different states of the world in which I have some underlying truth, but I make 500 variables and 250 observations. I do it again, I do it again, I do it again, I do it again. It works in every state of the world, almost surely. It always works. In a state of the world, it just corrects it.
On a fixed data set,
Yeah.
you do your shrinkage procedure once, and then you do it again using another reference point as the shrinkage.
Oh, another
Does that
reference
work?
point, another reference point.
Random point, yeah, on the sphere.
Okay, so you want to, I see. So you want to go back to here and you want to put a point somewhere else?
Yes, as
I
a
would use
reference.
this, I would have to, there is an optimal improvement. I would have to modify the formula slightly, and I can explain. The amount that you want to drag in here depends on it depends on the angle between this and this. It also depends on how dispersing this vector is. These things act as coefficients in laws of large numbers. So if I'm here, this is a very good point, 1 over root p, 1 over root p, 1 over root p. As this thing becomes lumpier and more concentrated, my correction actually becomes a little bit slower to be affected, and maybe it becomes.
It's not a random point in that sense. It's like a well-chosen point, so that this
Well,
modification.
It's not for this talk, but
Yeah.
for every optimization point, there's an optimal choice of this,
Yeah.
and then an optimal amount to correct. And in any direction, you can improve somewhat toward getting toward that B. But for a given optimization problem, the direction in which you would pick to correct depends on what the constraints in the optimization are. So it works for every point, and it works. But this amount that you shrink in is determined by a formula. It's not iterative. It's just a formula that I can write down.
Thanks.
Sorry, just a related question. Having small text a certain assumption, looks like some kind of signal to noise ratio or something. Can you unpack that a little bit?
The signal to noise ratio, so
Where beta squared over p tends to, you're sort of assuming that beta squared grows proportionally with p.
yeah. So well, think of betas as factor loadings. Okay, so I have y equals, or r, I think I called it beta f plus epsilon. Now let's suppose my beta was 1, 0, 0, 0, 0, 0, 0, 0. That's not a very good factor model because I'm not using, I'm not really distributing. So this assumption, yeah, there's a lot of assumptions. But this assumption is that as I grow in dimension p, my factor loadings are not concentrated in any particular set of dimensions, that they're sampling enough dimensions. And the reason for that is that these things act as coefficients in laws of large numbers. And if you want that thing to, if you want something to go to 0.
beta's a p vector, right?
Beta's a p, well,
And
beta's a
that's
p
the norm?
vector and p is a variable.
So beta squared is the norm of beta squared, or what is it
Beta,
exactly?
yes, that's a typo.
Okay. So you're basically saying that I have like a constant sort of signal in every coordinate vector on average. Okay. Thanks.
Question. I haven't got my phone. What time is it?
It's 10 to 5.
So this is an experiment a lot like the Bianchi experiment, except that we used simulation, which is described down here in more fine print, 400 simulations, a one-factor model. And here again, we looked at tracking error, and we looked at variance forecast ratio. And when we used a regular old PCA model, we found that we were getting, similar to Stephen's experiment, around 3% of tracking error and a little bit below 70% of the variance of the optimized portfolio forecast. When we corrected the PCA estimator by putting in better eigenvalues, and we explain in the paper exactly how we do this. It follows something called the S-Poet model of Fan and Wang, which is a standard correction. It did no good. The portfolio stayed far, the optimized stayed just as far from the optimal as it did when we didn't do the correction, and we continued to get around 70% of the variance. But when we corrected now with the JSE estimator, we were able to get closer to the portfolio and bring the variance forecast of the thing we had closer to where we wanted it to. This is, I think, p equals 500, and n equals, that's another typographical error. That one should be 250. But these are fairly standard sizes in finance, where we take a year's worth of daily data to estimate a covariance matrix, say for the S&P 500 or the Russell 3000, or even bigger universes. So it's the same sort of effect that we saw 6 years ago when we put in the corrections from an oracle. These are corrections. Okay, so I have just a few minutes to talk about Charles Stein, who in 1956 did something remarkable, just like Harry Markowitz did. He showed that sample average, in some sense, I think sometimes all of statistics is taking one kind of average or another. Charles Stein showed that the sample average in dimension greater than 2, or depending on whether you do what the mean, greater than 3. In the original paper, it was greater than 2. He used a 0, was not admissible, meaning that the sample average did not, in its dimension, minimize the mean squared error. He, and on his own first and later with Willard James, introduced a way to shrink a family of sample averages in toward their collective average. This is a clip from a paper from 1977. So even if you're a baseball fan, if you're not old enough, you may not recognize some of these names. But these are baseball players, and these are their observed averages at a certain point. And the James-Stein estimate shrinks them in by a definite amount that the James-Stein algorithm tells you to shrink them. And these James-Stein estimators tend in many circumstances, not in 100% of circumstances, but usually are much better than the sample. This was certainly like a shocking result in statistics. here's a quotation from Nobel laureate George Stigler. When this phenomenon is first encountered, it can seem preposterous. This is because the algorithm doesn't have anything to do with the nature of the elements that I'm shrinking. If I added to the baseball averages the fraction of rainy days in Peoria, I'd be shrinking that too. There doesn't have to be any connection between them. But the intuition for this, why this works, is that when I think of an estimate, if I think of a family of estimates, if I think of the largest ones, they're big both because they're estimating something big and because they have an error in it that it's big, and small things are small because they have something, you're estimating something small and they have a small error. So you might think that larger things tend to have larger errors and smaller things tend to have smaller errors, and by shrinking them in on average, you get closer to the truth. Kind of heuristic, but it's in my mind when I think of James-Stein. The way the James-Stein algorithm works is that you take your average and you shrink in by a constant. As written here, your constant takes the form of 1 minus a noise term, which is generally specified exogenous to the problem, to the variation in the observed. Our algorithm is identical, which we didn't know till about 2 years ago. This was first observed by Alex Skolnick in 2022, that you can write the algorithm this way. You take the average entry of the eigenvector and shrink toward it by a constant. The constant is 1 minus a noise term over the observed variance. And then, of course, if you want to stay a unit vector, you have to normalize back down, but you just divide it by its length. And an interesting point, always good to finish up with open questions, is that the nature of these two noise terms are very different. This is exogenous. This is intrinsic to the problem. It takes the form of a relative eigengap between the largest eigenvalue and the average of the remaining non-zero eigenvalues. And I can write down what the formulas are, but I'm not exactly sure why this eigenvalue, which itself does not corrupt optimization, in fact is used to correct the eigenvector that does corrupt the optimization. But here it is. You kind of lift the thing up into the plane, do your James-Stein shrinkage, and project back down. And that's exactly the formula that we're using to create those eigenvector approximations. So some work in progress, just clips from papers that aren't out yet. There are lots of papers in our we have a published paper in PNAS from January, which has no proofs in it, and in its references are papers with lots of proofs in it. These are some works in progress, and I've taken the liberty of adding Chaim's paper to this slide. I didn't ask. It's okay, because again, it's the same kinds of ideas going in directions that I hope you'll all learn about and read about. It's really great, and here are some of us working on this project. Stephen Bianchi down there, who set us on our way.
I guess we have time for a few more questions, if there are some. I guess I can begin. I'm kind of curious about the multi-factor extension. You were talking mainly, maybe this is Mike, I'm curious about the multi-factor extension. You were talking mainly about the single spike case. Can you tell us a little bit about that?
Yeah, so I've seen a preliminary manuscript of this. It's by Alex Skolnick and Hubeb Grudegan. And I think the main point is that you cannot treat, well, in a multi-factor model, you can shrink the largest eigenvector and leave the other ones alone and still make some progress. If you shrink them all as a group, you get more progress, and that's the nature of their algorithm. They're It's not all in my head, but I do know that it's important to think of them as a block and not as an individual in order to get the optimal results. From the very beginning, we've experimented with multi-factor models and just shrunk the leading eigenvector because we knew how to do it. And it certainly does make a good difference. And there's a practitioner paper that we have with published examples of this. So it works somewhat. Of course, in reality, when we're in finance, we don't really know how many factors are actually there, and a lot of all these simulations take great advantage of things we know. Yes?
You have a question.
So I have a question about that Bianchi experiment. One is when he corrects the eigenvector, is it just the leading one, or is it?
Just the leading one, but that was in a one-factor model. It was just the simplest possible case we could do. But we were expecting that by putting in random matrix theory type corrections on eigenvalues, or putting in the correct eigenvalues, should have helped us. And it didn't help us. If you write the formulas in the one-factor model, sounds like such a simple thing, but actually the formulas got pretty complicated in a hurry. If you write the asymptotic formula for what the variance of the optimized portfolio looks like in a one-factor model, you'll see the eigenvalue drop out of the formula. It goes up with 1 over p squared. It just leaves. It doesn't matter.
Another question is, I missed it. I think it's just probably me. That how the different replicate in that experiment were used?
How does
the different replicate? So they have. He created many p by n data set, right?
Yeah. Oh, how did he do it?
No. How did those replicate used?
How do you replicate them? Well, I have a random number generator.
Oh no. I mean how you.
Oh, how many times?
No. I mean how the different universe were used to.
I apologize. I'm not under. Do you understand the question?
Process, really different colors.
Oh, that was a long time ago.
Yeah, here.
Yeah, here.
And then you see, so the simulated data, so it seemed like from the different colors, and correct me if I'm wrong, right? Like these are different data generating processes, right, to create different data sets. So
Well, it's the same underlying statistics, but they're different. They're different data sets driven by the same underlying process. So they differ only by sampling error. And so, if you have a random number generator and you're generating 100 mean 0, variance 1 normal variables, you get one, then you get another, then you get another, and they'll be different. They differ by sampling error. So here we were creating fake returns to securities. 200, each one of those was, say, 250 returns to 500 securities. And they all had the same underlying distribution, but they were different realizations.
The average of the tracking errors to evaluate the performance? Is that
Oh, no. These are, I should have explained. These are box plots. So the 1,000 simulations generated that range.
I see. Yeah,
Those are, we box plot the results.
So we should probably wrap up. So let's thank Lisa again for a great talk.